Dark matter is cool. It doesn't interact with electromagnetic radiation. We know very little about it. We can't see it, but you sound really smart talking about it. You've definitely heard of it before and maybe didn't fully understand it, so let's go through how and why we think it exists.
We'll first start by looking at galaxies. Our Sun lies in the Milky Way, a large barred spiral galaxy formed of around 100 billion stars, gas and dust, all gravitationally bound. The Milky Way is composed of four main components: a nuclear bulge, a disk, spiral arms, and a halo. We assume most of the mass in the Milky Way lies in the centre, much like how the mass of the Sun makes up most of the mass in our solar system. All of the galaxies we have observed rotate. Just as planets orbit our Sun, stars rotate about a point known as the galactic centre. These stars must have a rotational velocity to maintain a stable orbit. This is necessary to balance the inward pull of gravity. Without it, galaxies would collapse. The velocity of this rotation can be measured using Doppler shift. Stars emit radiation in the electromagnetic spectrum. The recessive velocity of a star relative to the Earth causes shifts in the observed wavelength of this incident radiation.
We suppose the galaxy can be analogous to the solar system, in that the stars orbit around a central point similar to our planets. Since we can use Newton's gravity in the solar system, we will extend it to our simplified model of the galaxy. Let's have a quick look at how we expect the orbital velocity to behave equating the two forces, centripetal force and gravitational force. So we can see that v is proportional to 1/r. This means the stars in the disk should be slower and those closer in the bulge will be much faster. If we plot a graph of this velocity against the distance away from the centre, we see this is a characteristic curve. If we only consider stars to move in this way, then the rotational curve seems right. The velocities and the forces are as we expect. So here we have a model representing the stars in our galaxy orbiting about a centre, shown as the yellow sphere. The red star is orbiting about 21 meters per second, and the blue star has an orbital speed of about 35 meters per second. Keep an eye out for these speeds. Now here is the curve we get when we use observed velocities. This is interesting. There's a clear discrepancy which suggests, in reality, stars don't follow Keplerian dynamics as we would expect.
The only way that this could be the case is if mass is not concentrated near the centre as we first thought. Evidently, there is some additional mass present and very diffusely distributed which we have no real way of seeing. Only mass could affect motion gravitationally like this. Here we have another simulation of our galaxy, this time including dark matter represented by white points. There is a smaller net force acting on the star closer to the centre due to the dark matter. For the outer star, there is only an attraction to the centre. For this reason, the inner star now orbits slower at around 30 meters per second, and the outer star orbits faster at around 34 meters per second. In reality, it is not this simple. Dark matter is continuously distributed in a halo surrounding the galaxy.
Earlier we didn't talk much about the halo component of the galaxy, so it is a possibility for the dark matter to reside in this region, similar to the way we described it in the model. Dark matter could be a new type of particle, leading to a whole new understanding of physics. We still don't know what it is, though we do have fairly strong evidence for its existence. We've just seen how the rotation of our galaxy specifically shows that there must be some sort of matter. Now you know a little bit more about why we think dark matter exists. But if you want to have a look at other methods, have a read about gravitational lensing as another reason for why it exists.